Good morning, students. So in our last video we saw the properties related to our S matrix. So about the first property as well as the second property. Now we'll see the next property, the third one, that is the unitary property for a lossless junction. So I consider unitary property for a lossless junction. Now in our first property we had seen that the diagonal elements we are considering it as 0. Why? We had seen in the second property it was the symmetry property. You know that you had to prove the transpose of the S matrix is equal to your actual S matrix. So next is about the unitary property. In this unitary property we are considering it for a lossless network. So for a lossless network, the sum of the products of each term of any one row or column. You have a matrix, the consider two matrices. Let it be our S matrix itself. The S matrices, if I am multiplying this column with the complex conjugate of this column of S matrix itself multiplied by its complex conjugate, then it should give unity. Fine. It need not be a column always. If I multiply the row with its row itself, both are our S matrices. If I multiply this with the complex conjugate of those elements itself, so what should I get? I should get it as unity. This is what the unitary property means. So for this, we'll start with the derivation. Initially, what I have to consider is I have to consider a lossless network. For a lossless n-port network, the total power leaving the n-ports must be equal to the total power input to these ports. You know the property of power. Whenever the network or anything is a lossless one, whatever the input power that you are giving, that should be taken by the load, right? The same thing you are imagine here. For a lossless network, n-port network, the total power that is leaving the n-ports must be equal to the total power input to these ports. Fine. So if that is the case, what is the expression for that total power can be given as? The powers are nothing but the, when we are speaking about the powers, it is the reflected power with the incident power, right? So I can consider it as summation n is equal to, we know that there are n ports, so I'll consider it as capital N. Fine. Now it is reflected power should be equal to the incident power. Reflected power is given by Bn magnitude square. So Bn magnitude, whenever we speak about the power, we consider the magnitude square, right? That we already seen in our last classes. So this will be equal to summation n is equal to, because it's the total power, that's why I'm considering the summation n, its magnitude of an square. Fine. Now, what is this Bn? B can be replaced by, we know that B is equal to S into A, right? This we had already seen. So, what I can write this as, it is summation n equal to 1 to n summation. I will consider a new limit, because you know that here, we know that here what I have to consider, it is summation, because if B is our column matrix, A is also a column matrix, but S is a I can say it is an n cross n matrix, right? So I have to consider n variables here. So what I have to do here is I have to consider with a new variable. It is I is equal to 1 to n. I will consider that is S n I. It is AI power square. if you are confused here, I can tell you, check your notes or the previous video where we had considered b1 is equal to s11a1 plus s12a2 plus s13a3 and so on, right? So if my n is one of the variable, that first term n is a fixed one, 1 everywhere. Now this I is varying with 1 to n, right? That is this n. Fine, if it is 2 you will get a different, if it is 3 you will get a different, and so on. So consider that changes, understand it properly. Now this is equal to summation n is equal to 1 to capital N magnitude of an square. Fine, what next we can do here? Now we can consider it as, now this is one assumption we are considering. If only the ith port is excited, that means excited in the sense I'm giving the source to the ith port, rest all ports are acting like a match terminated. If that is the case, what happens? All my ANs will be equal to 0. All my ANs will be equal to 0 except only at AI. Rest everywhere my AN will be equal to 0, because whenever you are considering it as a matched one, you won't get any reflected wave from that particular port. When you won't get the reflected wave from that particular port, you will get your A as equal to 0, but only at your source end your A is not equal to 0. So this expression can be written as summation n equal to 1 to n. Now this will be, it is our Sni magnitude square into AI square, which is equal to, I have removed the summation. Why did I remove the summation? Because I is a fixed one. I can say it is the first port which is given with the source. So I is not at all a variable over here. So I is a fixed one only at that port. So I can say I have only one AI, right? So that's why we are considering it as expression like this. Now this is equal to summation n is equal to 1 to n magnitude of an square. Even this can also be written as summation. I need not consider this summation. Without considering the summation, I can simply consider it as, it is AI magnitude square. Why it is AI magnitude square? Because if you expand this, it will be A1 magnitude square plus A2 magnitude square plus A3 magnitude square and so on, right? But in all these terms, if I consider only at the first port I am considering, or I am giving the source, rest everywhere it will be equal to 0. What remains is A1 square. That's why I have taken it as AI square. Why did I? Because ith port I am giving the source. Fine. Now here the variable is n, so my AI square acting as a constant which can be taken outside the summation. So this can be written as AI magnitude square is equal to into summation n is equal to 1 to n magnitude of Sni square is equal to magnitude of AI square. Now these two magnitudes of AI square get cancelled. What remains is summation n is equal to 1 to n magnitude of Sni square is equal to 1, right? So in the next step, this is also equal to summation n equal to 1 to n. Whenever you speak about anything like I can tell you something like you have A plus JB. We have A plus JB. A plus JB, the magnitude square. What is the magnitude square of this? Magnitude square is nothing but square root of magnitude square. Magnitude is A square plus B square. It's a square. So square root with the square cancels. What will be there as a square plus b square. Right, now I have the complex value as a plus jb. Now if I write the complex conjugate of this and if I multiply that, that is a plus jb, multiplying it with its complex conjugate, that is a minus jb is a complex conjugate, right? If you multiply these two, what you will get, it is a square plus jab minus jab plus minus j square, which is minus 1, that becomes plus 1 in plus b square. So these two get cancelled. What remains is a square plus b square. Is it same as the magnitude square of your complex number? Right? So what I can write this as, this can be written as magnitude square, that is also equal to SNI into SNI complex conjugate. That is because of this. What answers you are going to get are equal. So this is equal to 1. This is what it means. You are considering the, if I multiply the S matrix, if I multiply any row with that row itself with its complex conjugate, then I will get it as a unity. Fine. So one more thing from this, another expression what I can write is summation n equal 1 to infinity Sni into Snj complex conjugate will be equal to 0 when I is not equal to j. So that means that if I consider any one row of my first S matrix and if I multiply it with some other row or column of that same S matrix with the complex conjugate, I will get it as 0. This is what it says. In another form, I can write this as S complex conjugate, S matrix complex conjugate into S transpose will give you U. That is the identity matrix. Or this can also be written as S complex conjugate is equal to, if I take it to the other side, that becomes S matrix transpose power minus 1. Even these are called as your unitary property. I hope you all understood. Next we'll see the last type of property, that is the phase shift property. Phase shift property.